Welcome to the Deep Dive, where we take your sources and extract those critical nuggets of knowledge. Our mission today is, well, pretty exciting. We're looking at how to make large reasoning models smarter and way more efficient, critically, without losing accuracy. We're diving into a paper called Adaptthink. Reasoning models can learn when to think.
Yeah, it's fascinating because, the usual thinking is more thinking time for these models equals better results, right? But this paper really challenges that. It highlights this crucial trade-off between how deeply a model reasons and the actual cost, the inference overhead.
Inference overhead. So like the compute power needed and the time you wait for an answer.
The latency.
Exactly. Compute, energy, latency, they can all become real problems if a model is sort of overthinking everything.
Okay, let's unpack this problem of always thinking. We've seen these amazing models like OpenAI o1, DeepSeek R1. They do complex stuff using these long chains of thought.
Right. They explore, they reflect, they check their own work. And that thinking process, it definitely gets high accuracy on hard problems, no doubt. But the cost.
Yeah. Big computational load, long waits for answers. And it begs the question, is all that heavy lifting always needed? The paper makes a great point. For simpler questions, where you want a quick answer, these models often go through way too many steps.
Like writing a whole essay when just the final answer was needed.
Pretty much. Unnecessary details, maybe trying things that obviously won't work for a simple case. It just makes for a worse user experience sometimes.
So it's like AI analysis paralysis.
Yeah.
And the usual fixes, they don't quite solve it. They still make the model think hard all the time.
That's basically it. People tried things like penalizing long answers, but the core issue was applying this heavy thinking mode universally. The real breakthrough started with something, well, almost deceptively simple. They called it no thinking.
No thinking. Okay, what's that involved? It sounds like you just turned
Almost. It's elegantly simple, really. They prompted the model with an empty thinking tag. Basically just think, just signaling. Skip the long reasoning part, go straight to the answer.
Okay, that is simple. And did it work?
This is where it gets really interesting. They did a pilot study on the MAP H500 dataset math problems sorted by difficulty. And for the easier problems, say level 1 to 3, no thinking actually got similar or sometimes even better accuracy compared to full thinking.
Their accuracy with no thinking. How?
It seems on those simpler problems, the long chain of thought process might sometimes introduce errors or get tangled up. Plus, the token usage just plummeted. We're talking response length dropping from, over 2,000 tokens to maybe 300 on level 1 problems. Huge difference.
Wow. Okay, so less thinking was better for simple tasks. That flips the script a bit.
Completely. It suggests thinking really pays off only when problems are genuinely complex. For easier stuff, it might even be counterproductive. And that observation was the key. It led to the core idea. Could a model learn to choose, to adapt its thinking mode based on how hard the problem seems?
Right. Learning when to think hard and when to just answer, that sounds like the goal. And this is where Adaptthink comes in, using reinforcement learning for this.
Exactly. Adaptthink is the RL algorithm they developed. It has two really key parts. First, a constrained optimization objective. Basically, it encourages the model to use no thinking.
To be efficient.
To be efficient, yes. But, and this is crucial, only if it doesn't hurt overall accuracy. It's maximizing efficiency under an accuracy constraint. They use a penalty weight, delta, to kind of dial in that trade-off.
Okay, so it learns to be lazy, but smart lazy. What's the second part? You mentioned a challenge.
Yeah.
The cold start problem.
Right. Models are usually trained just to think. They wouldn't naturally try no thinking initially. It's like they only know one way to solve problems. So Adaptthink uses an important sampling strategy during training. It forces a model to try both thinking and no thinking samples in roughly equal measure, like a 50-50 split in each training batch.
So it gets practice with both methods right from the start. It doesn't just default to the old way.
Exactly. It ensures the model explores both strategies and learns the benefits of each, preventing it from just sticking to what it knows. This exploration is key for it to learn that adaptive decision-making.
Makes sense. So let's talk results. They tested this on DeepSeek models, right? In different math data sets?
Yeah, DeepSeek R1 Distill-Quinn models, 1.5 billion and 7 billion parameters, tested on GSM-8K, that's grade school math, Math 500 for high school level, and even AMY 2024, which is much harder, Olympiad level stuff.
Good range of difficulty.
Yeah.
And the outcome.
Pretty stunning, actually. For the 1.5B model, average response length dropped by 53%, and average accuracy went up by 2.4%.
Accuracy went up while doing less work.
Yeah, and for the 7D model, length down 40.1%, accuracy up 2.3%. It's that counterintuitive result, again, efficiency and a performance boost.
That's really impressive. How did it stack up against other methods? And did it actually adapt, like use no thinking, more on easier problems?
Good questions. Yes, it outperformed baselines that only optimize within the thinking mode, showing the benefit of choosing the mode itself. And it absolutely adapted. On the easier GSM-8K and Math 500 sets, it used no thinking a lot more. On the really hard AIM set, it leaned much more heavily on thinking. For instance, level 1 math problems. The 7B model used no thinking almost 98% of the time. But as problems got harder, it intelligently shifted towards thinking.
That's exactly the adaptive behavior you'd want. What about that delta parameter you mentioned, the one controlling the trade-off? How sensitive is it?
So delta lets you tune it. If you increase delta, you push it harder towards no thinking, getting more length reduction, maybe slightly less of an accuracy gain, but still often a gain. It gives you that fine-grained control. But what's interesting is even with delta set to 0, no extra push for efficiency, the model still chose no thinking over half the time on simple problems.
Meaning no thinking is just inherently better for those cases, even without being explicitly rewarded for speed.
Seems so. The model learned the intrinsic benefit.
Okay, this sounds great for math problems. But what about, I don't know, writing an email? Or summarizing a document? Does this generalize? That's always the big question, right?
Crucial question. They tested it on MMLU. That's thousands of multiple choice questions, 57 different subjects, history, law, ethics, STEM, totally different from the math it trained on.
Yeah.
It held up. AdaptThink cut response length by over 30% on MMLU while keeping accuracy the same or even slightly better than the original models.
Okay, that's strong evidence for generalizability. It's not just a math trick.
Exactly. It shows the principle is robust. The model learned a general strategy for deciding how much effort to put in, applicable across domains.
So this really moves the needle. We don't need this monolithic, always think super hard approach. We could have models that are more discerning.
Discerning, adaptive, efficient.
Yeah.
It's about giving models that ability to make smart choices about their own reasoning process.
It really reframes efficient AI, not just faster, but intelligently faster.
I think so. It suggests maybe the next big step isn't just bigger models, but models with better metacognition. Models that understand how to think effectively for a given task.
Like teaching them not just the knowledge, but the strategy for using it.
Precisely. And that has huge implications for making these powerful models practical and scalable.
So looking ahead, what's the big question this leaves you pondering? Where does this adaptive thinking idea go next?
Well, I find myself wondering how far we can push this adaptivity. Right now, it's mostly based on, let's say, implicit problem difficulty. Could we make it respond to explicit user needs in real time? Like if you tell a model, I need a very quick answer versus take your time and be thorough, could one model dynamically adjust its entire thinking style based on that kind of interaction, beyond just thinking versus not thinking?
Adapting not just to the problem, but to the user's context or stated needs. That's a really interesting direction. Definitely something for all of us and for you listening to think about how these principles of adaptive reasoning could reshape the tools we build and use every day.